Our learning objective here has the keyword calculate in it. Calculate expected values, variances, and standard deviations, and demonstrate their application to investment problems. All right, to help understand why we consider probability to begin with, this is our key point here. Investment decisions are made under uncertainty. We don't know what the future is going to be, but we have certain ideas of the types of futures we may have, and we may assign certain probabilities to it, and we may say, if we get this type of scenario, this is the type of outcome we would expect, would have earnings per share of, let's say, $3, but if we get this type of outcome, maybe we'll only get earnings share of $2, and then we assign probabilities to those outcomes, and from those probabilities, we can come up with some idea of what we would expect. So the expected value of any random variable, which we denote as E of x, E bracket x, the expected value of x, is a probability weighted average of the possible outcomes. We already know how to calculate an average, right? It's the sum of all the xi's divided by n. That is the same as saying it's 1 over n x1 plus 1 over n x2 plus 1 over n all the way to xn. So in essence, the average is a probability weighted average where each probability is the same. But what if they weren't the same? What if we had a series of possible outcomes all with different probabilities? Well, here's how we calculate the expected value of x. It's the probability of x1 multiplied by x1 plus the probability of x2 multiplied by x2, and on to the probability of xn times xn, which is what I just did here, 1 over n. Let's say n is 10. Well, this would be the probability of x1 would be 10%. The probability of x2 would be 10%. The probability of x3 would be 10%. So it's the same thing here, except now we're considering the fact that maybe there are different probabilities, right? And from all of the different possible outcomes that x could take, because it is a random variable, and since it's random, it could take on a bunch of different values, from all of the different possibilities that it could take on weighted by their probabilities, we'll get one value that we feel is the expected value. And on top of expected value, we also want some idea of the range of possibilities, the distribution. So we would calculate the variance of a random variable. Notice it is the observation x1 minus the expected value squared. So we still have all the squared deviations, but we're weighting them by the probabilities. And again, if it were equal, all of these would be 1 over n minus 1. 1 over n minus 1. Because remember, when we calculate standard deviation and variance, we divide by n. Sorry, when we calculate variance, we divide by n minus 1 because we're using a mean in our numerator. We lose a degree of freedom, and then we take the square root of that for the standard deviation. Well, this is just saying, okay, well, what if it isn't 1 over n minus 1? What if the probabilities aren't equal? What if they are different probabilities? It would be the same probability here that we would use down here. So it may help to see this in action, and we'll see this example a little later on when we introduce conditional expectation and conditional probabilities. But let's say that we're looking at earnings per share for a company that could take on the range of $2.60 all the way down to $2, and we have different probabilities associated with those outcomes. What is the most likely target that we should aim for? Well, what should our expectations of earnings per share be? Well, it would be the probability times the outcome. So there's a 15% probability we'll get 260, 45% probability of 245, 24% probability of 220, and 16% probability of $2. If you multiply that out, you get 2.3405. And based on a probability tree, because that is the first part of our title here, that is what a probability tree looks like. All the different branches, all the probabilities must sum to 100%. So all of these probabilities must sum to 100% for the tree to be valid. We have an outcome at each step along the way, and we can calculate the expected value. There it is. To calculate the variance, it's the same probabilities. There's 15%, 45, 24, and 16. But we have our squared deviations in here. It's our observation minus the expected value squared. Same here, expected value squared. If we had equal probability on all of these, 0.25, this simplifies to the formula we saw for variance earlier. We get 0.03875, that is our variance. We know if we take the square root of that, we will get our standard deviation. And this would round up to 0.2. So our expected value is $2.34 with a standard deviation of 20 cents. Next, learning objective, formulate an investment problem as a probability tree. So we'll learn how to draw a probability tree and how to fill in the tree, and explain the use of conditional expectations in an investment application. All right, everything we need to know about this learning objective, it can be found in this tree diagram that I have. So let's begin with the first branches. We have S and SC, scenario and scenario complement. And these must be mutually exclusive and exhaustive. That means that the sum of their probabilities must add to 100%. Now, depending on where you've seen this before, and some of you might have seen probability before, you might see them referred to as E, or events, so that one of the branches of the trees might be called an E, or be called an event, as opposed to a scenario. Doesn't matter, means the same thing. So let's say scenario S happens. Under that scenario, X1, X2, and X3 could possibly be the outcome. And again, X1, X2, X3, much like S and SC, must be mutually exclusive and exhaustive. Exhaustive meaning the probabilities of each of these, of any of these, must add up to 100%. Because if we have scenario S, then we have three possible outcomes. Well, those probabilities must add to 100% here. Same with the probabilities with X1 to X3 if SC happens instead. We can calculate an expected value of X given S. That is the expected value at this point in the tree. And we've already seen how to do that. It's a probability multiplied by an outcome plus the probability multiplied by X2, except here the probability is a conditional probability. Because X1 can happen here and X1 can happen with S complement, we want to be specific about which probability we mean. So this branch right here, I'm going to circle it in pink. This branch up here, the probability of that occurring is the probability of X1 occurring given that S has occurred. Because for X1 over here, we see it's the probability of X1 given that S complement has occurred. That would give us the probability associated with that branch. And we do the same thing for X2 and X3. And that will give us the expected value of X given S and the expected value of X given S complement. Well, this stick right here that we see, that straight up and down line, that is the conditional operator, the probability of X1 given S. Well, we see the same thing in here, so that we have a conditional expectation. If this creates a conditional probability, the conditional operator in an expected value creates a conditional expectation. Once we have this conditional expectation and the other conditional expectation, we can calculate an unconditional expectation, which is nothing more than the probability of this outcome multiplied by the outcome, and the probability, SC, of this outcome multiplied by that outcome. We already saw that on the previous screen. We can also calculate the probability of X1 happening. Let me just erase some of these circles that I drew on the screen so that we have less to worry about here. And I'm going to circle X1 in white. Notice that it happens twice. So how can we calculate the probability of X1? Well, to get to X1, we first have to have scenario S, and then the probability of X1 given S. Then we have to have the complement of S, then the probability of X1 given the complement of S. So we just multiply the probabilities for X1 here and add them to the multiplication of these two probabilities. So it would be the probability of X1 given S, right here, multiplied by the probability of S, that's this probability, plus the probability of x1 given SC, which is over here, multiplied by the probability of SC. And we do the same for x2 and the same for x3. These are called unconditional probabilities of x1, x2, x3. All right, let's revisit that earnings per share example with the extended tree. We are given two scenarios in the example. Interest rates could be declining. There's a 60% probability of that event occurring. Or interest rates can be stable with a 40% probability. If interest rates decline, earnings per share could be $2.60 or $2.45. We assign a 25% probability of $2.60 happening and a 75% probability of $2.45 happening. Notice now, declining rates or stable rates, the probabilities add up to 100%. Here we have 25% and 75%, probability adds up to 100%. If we have stable rates, earnings per share could be $2.20 with a probability of 60% or $2 with a probability of 40%. Notice those add up to 100%. So our tree is valid because the probabilities at each stage, at this stage add up to 100%, and at each branching here and here, each branching outwards, the probabilities add up to 100%. We can calculate the probability of 260 happening. It is just the multiplication of two probabilities, 0.6 times 0.25, 0.15. The probability of 245 happening, we have 0.75 times 0.6 or 0.6 times 0.75, however you, whether you read the tree forwards or backwards, 0.45, 0.24 at $2.20, and 0.16 at $2. These are the probabilities we saw earlier. Now, these probabilities, if our tree is constructed properly with 100% probability at each step along the way, the total of all of these, because we're multiplying everything, should also add up to 100%, and it does. We know we have a valid tree if everything adds up to 100%. And we can calculate our expected earnings per share. We can do it in two steps. We can calculate a conditional expectation here and a conditional expectation here, then calculate an unconditional expectation, or we could just do it all in one step. Remember, to calculate the expected conditional value here, we multiply this probability by this outcome. Well, this probability is the conditional probability, right? It's the probability of x1 given s, and we multiply it by x1. Once we have this value, which is the combination of these two, we multiply this probability by this expectation. There's that probability. And we do it for x2 in scenario S, 260, 245. We'll do it for x3, which is 220. We'll do it for x4, which is $2. Multiply that out. I put all the values down here, and we've already solved it earlier to be 2.34, I think 2.3405. So we have solved that earlier using these probabilities with these outcomes. But these probabilities, note, are these first two items in each of the following terms at the bottom of the screen. Next, learning objective, calculate and interpret. Pay attention, you have a calculate there. Calculate and interpret an updated probability in an investment setting using Bayes' formula. Right, our next LOS, calculate and interpret an updated probability using Bayes' formula. And I'm going to show you using a tree how super easy this is. I don't like this version of the formula that they provide. It is the same as this formula, except the probability of S is just broken out. I prefer a probability divided by a probability as opposed to a ratio multiplied by a probability, and I'll show you why it makes a lot more sense that way. Let's figure out what we're doing here. Bayes' formula, what is that? A method for updating prior probabilities based on new information. So up to now we have scenarios, and from scenarios we have specific events on each one. So this event over here can happen in two different ways. And we have these probabilities of scenario versus scenario complement. And we have some probabilities on them. Those are called prior probabilities, which we see down here in the example I give down here. These are called prior probabilities. We start with the probabilities of these scenarios, and then we have probabilities of events based on which scenario happens. So these over here are all conditional. This is the probability of the event, of course, given whatever scenario there was. Bayes' formula says, well, hang on here. Let's assume for a moment that we already know what event occurred. And if we know what event occurred, would we change our probability of the scenario based on what we started with? So it's asking us to calculate the probability of a scenario given that an event has occurred. So we get to see the event first. That's the first bit of information we get. And from that, would we change our probability? And if we do change our probability, that is called a posterior probability. So we start with priors. We see the occurrence of an event, or maybe we only witness the occurrence of the event, and then we would change our priors based on Bayes' formula to create posterior probabilities. So let's walk into this nicely. Recall the total probability rule. The probability of E, or any event, is the probability of the event under every scenario multiplied by that scenario. The probability of the event under a different scenario multiplied by that scenario, etc. So given that we observe E instead of the scenario first, we observe E, what is the probability of the scenario? In other words, we want the conditional going the other way as opposed to going this way. The probability of the scenario given the event. And it is the probability of the event given the scenario multiplied by the probability of the scenario divided by the probability of the event. And then the book takes it one step further and says, take the original conditional divided by the probability of the event, then multiplied by the probability of the scenario. Notice that this is exactly the same thing. So why am I saying that this makes more sense than this? Let me show you. Let's look at this tree. We're looking at a company and we're placing probabilities on their EPS. EPS exceeding expectations, EPS meeting expectations, or falling short. 45%, 30%, and 25%. And we're saying, well, the company will expand, but depending on what their EPS is, we place a different probability on them expanding. If they exceed EPS, there's a 75% probability they'll expand, 25% probability they won't. If they meet expectations, that probability of expansion only drops to 20%, and if they fall short, there's only a 5% probability that they're going to expand. So what is the probability that they're going to expand? Right? Well, they can expand here, they can expand here, and here. So it's the total probability rule. How do we get the probability? We multiply 0.45 by 0.75. We get this probability. Plus 0.3 times 0.2. We get this probability. And 0.25 times 0.05. We get this. This is 0.3375. This is 0.06. This is 0.0125. Added up, we get 41%. So if I say to you, they've expanded, what is the probability that earnings per share exceeded expectations? You would say, well, that would have happened 33.75% of the time out of 41%. So wouldn't it just be 33.75 divided by 41? Yes. The probability of E given a scenario multiplied by the probability of the scenario divided by the probability of the event. There it is. When you put it out, and when you sort of make it the ratio and multiply by the probability, what you are saying instead is it's the probability, the conditional probability divided by the probability of the event, and then that ratio is multiplied by the probability of the scenario. It just doesn't flow very well linguistically. It just sounds better if you say, well, this would have been the resulting probability. This is the total probability. Let's just divide them. How do we update this one? 6 divided by 41. How do we update this one? 1.25% divided by 41. There we go. So that's what's done over here. 0.75 times 0.45 divided by 0.41. Or as the book likes to put it, 75 divided by 41 times 0.45. You get the same thing, 8231. I just think it looks better like this as opposed to this. That's it. That's all Bayes' formula is. Start with the total probability. You'll end up with a total probability. Find the probability of each of the subcomponents that add up and simply just divide them. And when you divide them, that will update all of the prior probabilities.